Okay, today we're going to do our last section in this analytical unit. We're going to talk about multiple angles formulas. We're going to look at the multiple angle formulas to rewrite and evaluate trigonometric functions, the power reducing formulas, and the half angle formulas. So we're going to start with our double angle formulas. Now the double angle formulas are actually derived from a formula we learned earlier in the unit, which is our sum formula, because I could write, for example, sine of 2 theta as sine of theta plus theta. So I'm using my sum formula. Now if you remember from our sum formula, that would be the sine of the first angle times the cosine of the second angle plus the sine of the second angle times the cosine of the first angle. And then you notice that there are two, if I add that together, 2 sine theta cosine theta. So that is our formula for sine of 2 theta. We can rewrite it as sine of theta times cosine of theta. Now you can do the exact same thing for cosine of theta, and you would end up with cosine squared theta minus sine squared theta using your sum or difference formula. But notice that I have a sine squared, so I could replace sine squared here with my Pythagorean theorem identity of 1 minus sine squared. Simplify that down, I get 2 cosine squared theta minus 1. Or I could have replaced the cosine squared using my Pythagorean identity. So again, we have 3 formulas that we can choose from when we're doing cosine of 2 theta. It doesn't matter which one you choose. For tangent of 2 theta, the formula we'll use is 2 tangent of theta divided by 1 minus tangent squared theta. So these are the formulas for your double angles, when your angle is doubled inside the trig function. There are a couple ways that you'll see us working with this. One way is with, back to our right triangle trig knowledge. So for example, let's say I'm given that theta is between 3 pi over 2 and 2 pi. So that tells me theta must be in quadrant 4. And so if theta is in quadrant 4, I know a little bit about this. So I'm going to go back to my right triangle, do my representative right triangle in quadrant 4. My central angle is angle theta. And I was given that cosine of theta equals 5 over 13, so that is my adjacent side over my hypotenuse. And I can find my missing side by using right triangle trig. And we can do our Pythagorean theorem here, and we'll solve this, and we'd get that y is equal to 12. Or you could realize that this is one of those Pythagorean triplets that you kind of see show up a little bit. Now notice I don't label the side 12, but I label it negative 12 because again, that's because I'm in quadrant 4 and my y is negative. So just by looking at this right triangle that I figured out here, I know my sine of theta is negative 12 over 13. Cosine of theta was given as 5 over 13. And then tangent of theta has to be, therefore, negative 12 over 5. So what I'm going to do is I'm going to figure out my sine of 2 theta by doing my double angle formula, which is 2 sine theta cosine theta. Now I'm going to plug in the information I figured out. Well, we know that sine of theta is negative 12/13 and cosine of theta is 5/13. Multiplying this all together, 2 times negative 12 times 5 will give us a negative 120, and 13 times 13 is 169. So my answer for the measure of angle 2 theta, sine of 2 theta, is negative 120 over 169. So I'm going to repeat that for cosine. Now, I have 3 choices of the cosine angle to use. How you can determine which angles. Notice I was given the cosine, so I'm going to use the formula that only involves cosine, just in case I made a mistake when I figured out my sine measurement. Just in case. It's the safest one to do, so I'm protecting myself a little bit. So I'm going to use the formula 2 cosine squared theta minus 1. And then I'm going to replace that cosine theta with 5 over 13, and I'm going to square that, minus 1. So 5 over 13 squared, 25 over 169 times 2, then minus 1 will give us a negative 119 over 169. Last, we need to figure out the tangent of 2 theta using our double angle formula for tangent. And recall that our double angle formula for tangent is 2 tangent theta divided by 1 minus tangent squared theta. So we already figured out that tangent was equal to negative 12 over 5. So I'm going to replace every tangent of theta with negative 12 over 5. Then I'm going to simplify this problem down. So multiplying the top, I'd get negative 24 over 5. And then on the bottom, I square, and then I'm going to add that. Subtract that from 1 and get negative 119 over 25. And then flip and multiply the bottom fraction, and a negative becomes positive, and I end up with 120 divided by 119. Okay, I want you to pause and figure out, given this information here, find the sine of 2u. Okay, first thing I'm going to do is identify what quadrant I'm in, just like I did before, so I know u must fall in quadrant 3. And that tells me what my trig functions are. So I'm going to draw my representative rectangle in quadrant 3, making my central angle U. And then take the given information that tangent of U is 8 over 15. Remember, tangent is opposite over adjacent. But remember, in this quadrant, x and y are both negative, so I have to label those sides -8 and -15. And then using my Pythagorean theorem, or recognize these are Pythagorean triplets, I know my hypotenuse is 17. So let's label what we know. Sine of u from the diagram is -8/17. Cosine of u is -15/17. And we already were given tangent of u. I just like to list them all together, so I have that to look at when I'm working these out. So sine of 2u, that formula is 2 sine of u times cosine of u. So I'm going to replace sine of u with -8/17. And I'm going to replace cosine of u with -15/17. And then I'm just going to multiply that together. And I end up with 240 over 289. Okay, now you figure out cosine of 2u. So cosine of 2u, since I was given tangent, I wasn't given either sine or cosine. It really doesn't matter which formula you use. I'm going to choose 1 minus 2 sine squared theta, just because I hadn't used it yet. But you can use any of the formulas you want. So I'm going to replace the sine of u with -8/17. Make sure you square that. And then doing my algebra, working this out, I end up that cosine of 2u is 116 divided by 289. Now, last one, try tangent of 2u. So recall the tangent of 2u formula is 2 tangent u divided by 1 minus tangent squared u. So I know that tangent of u is 8/15, so I'm going to replace everywhere I see tangent of u with 8/15. And then I'm going to simplify that equation down. And I get 240 divided by 161. A second approach that you'll see with using these double angles is solving trigonometric equations like we did in the last section. So notice here I have sine of 2x and I have cosine of x. I want to be able to get the angles that my functions are talking about to be the same. So I need to rewrite sine of 2x using my double angle formula. So now notice that I have sine x, cosine x, and so all of my trig functions have the angle x. And that's going to let us solve it. So I can factor out my GCF of 2 cosine x. Then I can set each of those factors equal to 0 using our zero product rule. Once I solve that, I ask myself what angle has a cosine of 0, and that would be my pi over 2 and 3 pi over 2. Then what angle has a sine of -1? That would also be 3 pi over 2. So since it didn't specify this within the which quadrant or my range, I got to include all values. So I would write my answer as either pi over 2 plus 2n pi, and x is equal to 3 pi over 2 plus 2n pi, or I could combine those two together because they're 180 degrees apart from each other, and just simply write pi over 2 plus n pi. Either answer is correct. Okay? Try to figure out what cosine of 2x plus cosine of x equals 0 is. Okay, so I'm going to replace cosine of 2x with 2 cosine squared x minus 1. I chose that formula because I had a cosine already in my equation. It was the only other trig function, so I wanted the same trig function. So you're going to kind of look at what you have to decide which of the three double angles for cosine formulas that you're going to use. So factoring this together as a quadratic, set each of those factors equal to 0. Solving each factor, I get cosine of x is equal to 1/2. And I know the angle that has cosine equal to 1/2 is pi over 3. And then cosine is positive in quadrants 1 and quadrant 4. And so the angle in quadrant 4 that has a reference angle pi over 3 is 5 pi over 3. And then I know the angle that has a cosine of -1 is pi for my unit circle. So my answer to this problem is pi over 3 plus 2n pi. X is equal to 5 pi over 3 plus 2n pi. And x is equal to pi plus 2n pi. Yet another way that you're going to see the double angle formula is in conjunction with our sum formula. So here I'm asked to find the sine of 3x. Well, sine of 3x is the same as the sine of 2x plus x. So I'm going to use my sum formula with my double angle formula. So it just keeps building. So recall that our sum formula is the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. And everywhere I see a 2x instead of just x, I'm going to use a double angle formula. So I get 2 sine x cosine x times cosine x, replacing cosine of 2x. And now I can choose any of those formulas, but since the direction said right in terms of sine, I'm going to choose 1 minus 2 sine squared x to replace that cosine of 2x times, again, the sine of x. Don't forget that. So I have 2 sine x cosine squared x. And distributing my sine, I end up with sine x minus 2 sine cubed x. And then, I can replace that cosine squared x with 1 minus sine squared of x, which I get from my Pythagorean identity over here in the think bubble. And so to get rid of my parentheses, I need to distribute 2 sine of x to everything inside that parentheses. And all that's left to do is combine my like terms. I have negative 2 sine cubed x minus 2 sine cubed x, and I have 2 sine x plus a sine x. So that ends up being 3 sine x minus 4 sine cubed x. Okay, we're doing a very similar process for this one. So I want to rewrite cosine of 3x as cosine of 2x plus x. And my sum formula for cosine is cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. So everywhere I see that double angle formula, I'm going to replace it. And again, it told us to write in terms of cosines. I'm going to use my cosine formula for the cosine of 2x. And then my minus 2 sine x cosine x for sine of 2x. Okay, simplifying that down by distributing the cosine to everything in the parentheses. And combining sine x to times sine x as sine squared x. Again, I notice that I have a sine squared x. I want everything in terms of cosine. So I'm going to replace that sine of x with my Pythagorean theorem. Okay, I have to do another think bubble. So I got sine squared x plus cosine squared x equals 1. And then solve that for sine squared x. And I figure out that I'm going to replace sine squared x with 1 minus cosine squared x. Okay, I got to distribute negative 2 cosine x to everything in the parentheses. I just realized I forgot to write my cosine. I forgot to write my cosine twice. Okay, let me fix this. There we go. So our answer should have been 4 cosine cubed x minus 3 cosine x. All right, so we have our double angle formulas that we've learned so far today. So our next thing we're going to do is called power reducing formulas. You'll use this quite a bit in calculus, especially Cal 2. So what this happens, if you have a trig function that's to higher power and you want to reduce the power, these formulas come in very handy. So sine squared u can be rewritten as 1 minus cosine 2u over 2. So I'm using my double angles here. And cosine of 2u is 1 plus cosine of 2u over 2. So remember that they always have a close relationship. Now to get tangent, remember that's just sine divided by cosine. So I'm just going to take my sine formula here, my cosine formula here, and we're going to divide them. And so when you flip the bottom one, the 2's just cancel out. And so I end up with 1 minus cosine of 2u divided by 1 plus cosine of 2u. So that'll be my formula for tangent squared u. If I need to get rid of my powers, which sometimes you'll need to do that later on in other math courses. But for our class, what we're going to use is going to be some practice of reducing this. So the directions here, we're going to reduce sine to the fourth x in terms of cosine. So first thing I say, well, sine to the fourth is the same as sine squared x quantity squared. So I'm going to replace sine squared x with my power reducing formula from above, which is 1 minus cosine of 2u divided by 2 quantity squared. And then remember, to square a fraction, you square the top and you square the bottom. So that's going to be 1 minus cosine of 2u times itself over 2 squared, which is 4. Now, just to make myself have a little bit more room, I'm going to factor that 1/4 out and just work with it as a single fraction. You'll do this a lot with these formulas. It just makes life a little easier to work with. I end up with another double angle, and I want it as a first power. So I need to replace that cosine squared with our power reducing formula for cosine of cosine. I made a mistake there. So I need to replace this. So I'm going to do 1 plus cosine of 2 times my angle, but my angle this time is 2u, so that's actually a 4u. So be careful when you're substituting that in, because our angle in this case was 2u. All right, so let's do some cleaning up of this and simplifying it down a little bit. Let's get rid of the fraction by distributing that 2 to each term. And then I'm going to rewrite that as 4u, or 4x in this case. All those u's should be x's. All right, now let's get rid of the parentheses by distributing the 1/4. Doing this so I can combine like terms and then find my GCF. I will eventually factor out my GCF. I'm going to combine my like terms, so 1/4 and 1/8 combined to get 3/8. And that's all I can combine. And then I notice I can take out my factor of 1/8, and then I can write what's inside the parentheses without all those messy fractions. And that's how we usually like to write our answers here. So my sine to the 4th x is equal to this answer. So we're going to start it doing the same way as we did the last one. So we're going to rewrite tangent to the 4th x as tangent squared x quantity squared. All right, and then replacing our power reducing formula for tangent, which is 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta, then distributing the square to the top. So that means I'm going to take the top times itself, and then distribute the square to the bottom, meaning I'm going to take the bottom times itself, and I'm going to multiply that out using our full method. Again, I have a cosine squared in both of those, so I need to replace cosine squared of 2x with our power reducing formula of 1 plus cosine of 2 times 2x divided by 2. And I'll do the same thing in the denominator. So I end up with 1 minus 2 cosine of 2x plus 1/2 plus 1/2 cosine of 4x. All over 1 plus 2 cosine of 2x plus 1/2 plus 1/2 cosine of 4x. Then I'm going to take the GCF out of the top and the bottom, which happens to be 1/2 for both of them. Oh, well, we need to combine our like terms of 1 and 1/2. Then I can take my GCF out. Of 1/2, and that leaves us with 3 minus 4 cosine of 2x plus cosine of 4x over, take out the 1/2 here as well, and we get 3 plus 4 cosine of 2x plus cosine of 4x. So our answer is simply 3 minus 4 cosine of 2x plus cosine of 4x all over 3 plus 4 cosine of 2x plus cosine of 4x. And those are some examples of how you would use the power reducing formulas in this course. Next, we're going to learn something called the half angle formulas. So here, if you have an angle divided by 2, you can apply this half angle formulas. So we're going to start with sine of u divided by 2. I could rewrite sine of u divided by 2 as plus or minus the square root of 1 minus cosine of u divided by 2. Now all that's underneath the square root, and notice I have a plus or minus here. This does not mean I got two answers, one positive, one negative. What this means is that I look at my angle u plus 2. And if that angle, the sine, if it's going to be a positive answer or if it's going to be a negative answer, is determined by which quadrant the original angle u divided by 2 lies in. The exact same thing is true for the cosine function. So it's the square root of 1 plus cosine of u divided by 2. Again, we figure out if that answer is going to be positive or negative based on the angle, the quadrant that u over 2 lies. Tangent, we don't have to worry about that. For our tangent, you have two possible formulas. One formula is 1 minus cosine of u divided by sine of u. Or the second formula is sine of u divided by 1 plus cosine of u. I'm going to rewrite that because that kind of looks like it might be a compound fraction, one fraction over the other. I don't want you to get those confused. These are two separate formulas, and you get to pick which formula to use. Okay, so let's see how we can use these to help us figure out this information. So I'm going to find the exact value of sine of 105. So this is a way for us to find some angles that's not on the unit circle using only a unit circle measurement. So first I'm doing sine. So first I look at 105 degrees. What quadrant is 105 in? Well, that's in quadrant 2. And is sine positive or negative in quadrant 2? Well, sine would be positive in quadrant 2. So I'm going to be using the positive instead of the minus when I do the formula. And then I need to figure out an angle that is on the unit circle that when I divide by 2 equals 105. So I picked 210. So I'm going to rewrite sine of 105 degrees as sine of 210 degrees divided by 2. And so using my power reduction, notice I'm putting out just a plus sign. I didn't put plus or minus because I figured out in this quadrant sine is positive. And then I'm just going to go, okay, I'm going to replace that cosine of 210 degrees with its angle measurement. So first off, I got to figure out the reference angle for 210 degrees. Well, that's 30 degrees is our reference angle. And then I need to think, okay, what is the sine of 30 degrees? Oh, sorry, cosine of 30 degrees. Well, the cosine of 30 degrees is square root of 3 over 2 from our unit circle. But then remember, 210 degrees is in quadrant 3. And so in quadrant 3, cosine positive or negative, well, cosine is negative in quadrant 3. So the cosine of 210 degrees is negative square root of 3 over 2. So I'm going to replace that cosine of 210 degrees with negative square root of 3 over 2. Then I'm just going to simplify. And now for the numerator, I'm going to rewrite 1 as 2 over 2 and then add that with my square root of 3 over 2. And that'll give me 2 plus the square root of 3 over 2. And then I'm still needing to divide that by 2. So when you divide by 2, that's the same as multiplying by 1/2. So I end up that 2 plus the square root of 3 over 4. And then the square root of 4 is 2. So I can bring that out of the square root. And so my final answer is the square root of 2 plus the square root of 3 all over 2. Whew. All right, now you try finding the tangent of 105 degrees. Okay, I'm going to start the same way. I'm going to remember my formula. My tangent is 105 degrees. Is the same. I can use the 210 degrees divided by 2 again. So that would be 1 minus cosine of 210 degrees divided by sine of 210 degrees. So we've already figured out cosine of 210 degrees. That was negative square root of 2 over 3. Now I need to figure out the sine, so that's going to be 1/2. And then in quadrant 3, is sine positive negative? Sine is negative in quadrant 3, so I will write a negative 1/2. And so I get 1 plus the square root of 3 over 2 divided by 1/2. Find a common denominator in my numerator term, that's 2 over 2. So that's 2 plus 2 divided by 2 times the negative 1/2, which I'll flip and multiply. And so my 2's cancel out and I get negative 2 minus the square root of 3 when I distribute that negative 1 to my what's left in the first parentheses, first fraction. So hopefully you got negative 2 minus square root of 3. Okay, as with everything else that we've been learning, we can also use these formulas to apply to our solving trig equations. So here is a trig equation. I'm finding the solutions on the interval from 0 to 2 pi. So first thing I notice is I have an angle that's not x, it's x divided by 2. So I need to get rid of that by replacing that with our half angle formula. So I'm going to replace, and I keep wanting to write pi. Okay, so I'm going to replace cosine of x over 2, which is my half angle, with my half angle formula. And because I don't know what x is, I got to put plus or minus. But luckily, I'm going to square this. And if I square a positive, it's going to give me a positive. If I square a negative, it's going to give me a positive. So my answer is just going to be positive here. I don't have to worry about the plus or minus because I'm squaring them. All right, so to square, when I square the square root of 1 plus cosine of x, that square and square root cancel each other out. And when I square the square root of 2, the square and square root cancel each other out, so I'm just left with the 2, and then the 2 cancels with the 2 outside. So I have 1 plus cosine squared x equals 1 plus cosine x. Now let's get that equal to 0, since this is a quadratic. And then we're going to see if we can solve this. I'm going to take out my GCF of cosine x, set each of those factors equal to 0. And when is cosine of x equal to 0? That is at pi over 2 and 3 pi over 2. When is cosine of x equal to 1? That's at 0 degrees. And so my answer for in my unit circle is 0, pi over 2, and 3 pi over 2. All right, you try the next example. All right, so first thing I see is that half angle. So I'm going to replace my half angle, sine of x over 2, with the formula we have, which is plus or minus the square root of 1 minus cosine of x divided by 2. And then we still need a quantity square that. So again, I don't have to worry about the plus and minus because it comes out from when I square it, it's going to all be positive. And the square root of 1 minus cosine of x over 2 squared is just 1 minus cosine of x over 2. So I'm going to multiply each side by 2 to get rid of the fraction. And now I'm going to get it everything onto the left-hand side so I can set it equal to 0 to solve. And this one I'll need a factor of the quadratic. But then you can set each factor equal to 0. What angle has a cosine of 1/2? Well, that's pi over 3 is my reference angle. And then I know cosine is positive in quadrants 1 and quadrant 4. So to find my other angle in quadrant 4, I just take 2 pi minus pi over 3, and I get 5 pi over 3. And then for the second factor, I end up that cosine of x is equal to -1. Which angle has a cosine of -1? Well, that would be pi. So my answers are pi over 3, pi, and 5 pi over 3 in my interval from 0 to 2 pi.